And my prayer. It'll be awkward for a second. Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at Uni of Adelaide. It's Semester 2, 2023, and this is a revision seminar for Statistical Practice I in all of its flavours for life sciences and vet bio and all the different versions of it. Okay, I've had a big chat with some people who are here and on the Zoom, and we are going to talk about whatever's on people's minds. And the first things on people's minds were sample size calculations from margins of error, and also how to decide what sorts of probability equations or other equations to use. And that's a big question, but we're going to get there. It sounds to me like it would be really useful to try and distinguish between the different kinds of things you're asked to do and how to tell when you're being asked to do them. That's sort of what you want to know, right? Yeah. Okay, well, let's see how we go. I can definitely talk about the sample size from the margin of error for one of the questions from online, and that will at least give me some time to let the back of my brain process the other question for a bit, okay? Might need a bit of a run-up to sort this one out. So I just want to talk a little bit about the idea that's going on here, just to make sure I'm on the same page that you are. So, margin of error is a terminology that I'm familiar with from doing confidence intervals. And confidence intervals are a statistician's way of answering a question of the type, what is this number? And in general, in this course, I think there are three, I could be wrong, so you might have to correct me. I think there are three confidence intervals that you calculate, maybe four. But the first one you calculate is, what is the mean? Like the population mean. So for example, so if the question is, now they won't say it this way, but this is the idea of the question that's being asked, okay? So this isn't the question that's in the exam paper. This is the question that the researcher is wanting to know. What does the population mean? And you collect data and you don't ever know what the population mean is. So your answer is the population mean is between here and here. So the answer, 95% confident is between blah and blah. That's the sort of answer that you give, right? Yeah. So it's just worth noting that whenever you want statistics to answer the question of what is this number that is in population based on the data in my sample, the answer is always a confidence interval. Okay, cool. And that's what confidence intervals are for. And confidence intervals are like between here and here, but the way you calculate them, so here's an idea, there's a number here and there's another number here, and you say between here and here, but the way you calculate them is you figure out a center and you go up a bit and down a bit. That's how you make a confidence interval. But you only report these numbers. But what you calculate is this number in the middle, and then a bit more and a bit less. And this distance here between the center and the edge, that there is called the margin of error. Let me actually do an example. Almost all the questions in that exam begin with the phrase "a researcher." So like, a researcher wants to estimate the mean. Make up something random, I guess. Mean weight of an avocado. It's great. What's this going to be, about 100 grams? 200? Pretty heavy. 200 grams. Let's say that. That's cool. Cool. She collects 50 avocados. Mean weight is 227 grams. With a standard deviation of, I don't know, 12.3 grams. Let's do that. But even before reading the actual instructions that I'm about to write, my first piece of advice that I'm going to give about reading questions is you have to understand the context in order to be able to answer the question at the end at some point. And so in order to focus your attention, I would recommend not reading the numbers to begin with. This is a strategy that is taught to people of lots of different ages, including school children. It's called the 3 reads, like 3 reads. And the first read is the story. And the second read is the details. And the third read is the instructions, like the goal. So here's the story. Researcher wants to estimate the mean weight of an avocado. She collects some number of avocados, and the mean weight was some number with a standard deviation of some number. I choose not to read those numbers at this time because they're just details. So the story is, I'm trying to figure out what the mean weight of an avocado is. Now, that is an what's this number sort of question. And so my expectation is, right from that first sentence, that I'm probably going to calculate a confidence interval at some point. And I know that the information I need to calculate a confidence interval is a mean and a standard deviation. But I don't really need to know what they are to know that that's what I'm going to have to do. And now I've got the actual details, and that's really not going to change the calculation that's done. Calculator is going to do that for me anyway. And then the actual instruction is calculate a 95% confidence interval for the mean weight of an avocado. Even if the lecturer had completely forgotten to put an actual instruction in here, I would still have calculated a confidence interval. Like if that bit cut off the bottom of the exam for whatever reason when they printed it, I would have said confidence intervals are designed to answer the question of what is the mean weight, and so I will calculate a confidence interval. So please don't do something they didn't ask you to do unless they didn't ask you to do anything. So yeah. Okay. So I'm now forewarned in my mind, even before I read that it was probably going to be a confidence interval based on the situation they set up. And that's one of the reasons to do the 3 reads. So the way that you calculate a confidence interval is to say something like this. We need some information to do a confidence interval. And this is what you would definitely put on that cheat sheet of yours so that you can look it up. But I can remember it just. So you may have to check for me just to make sure it's right. So I can say that I'm going to need some information. It's going to look like this. I'm going to need the mean. I'm going to need the standard deviation. I'm going to need the sample size. And traditionally, just I'm adding to this after the fact. Traditionally, they call this thing X bar, and this thing S, and this thing N. And it's a useful thing to do for yourself if it makes it easier for you to give the letters for them. I'm going to need one more thing in this confidence interval here. That's going to give me a T, probably a T star. So that's what I'm going to do. So my 95% confidence interval endpoints are the mean plus or minus T star times S on root N. Does that look familiar? Did you do T confidence intervals? Did they do T star? Is that how they wrote it in this one? Yep. Every degree has a stats course in it, and they all use different notation. So it's just worth me checking that that's how they did it. So this X bar they've told me, and this N they've told me, and this S they've told me. I'm going to have to figure out what the T star is. If I'm outside my exam, I would go ask a computer what that is. So I just have to imagine something. Wait, just let me stop and explain something about how confidence intervals work. They're intimately connected to hypothesis testing. So just as an aside, while I'm here. Confidence intervals and hypothesis testing are 2 sides of the same coin, or possibly the same side of 2 coins. To quote Tom Stoppard, they use the same data to answer the opposite questions. So hypothesis test answers yes or no questions using a p-value to help you decide whether the answer is yes or no. And confidence intervals answer what's this number questions. And so quite a few hypothesis test questions are, is the number equal to this option? So e.g., is the mean 200 grams? For example, that's a perfectly good yes or no question. That is the kind of hypothesis question that hypothesis testing can answer. And you would go through the whole thing of saying mu h naught mu equals 200 and blah, 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 blah. And you'd get, dot, 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 p-value equals whatever the p-value works out to be, okay? Okay. And that p-value will work out to be something. And based on whether that p-value is higher or lower than some cutoff, you will decide whether the answer to the question of is the mean 200 is yes or no. How do you feel about that description of how hypothesis testing works? Yep. Okay. So I can actually do that in a minute. I'm just going to look that up in a second. All right, but a confidence interval answers a what's the number question. Such as, what is the mean? You may notice that these 2 questions are quite similar. Is the mean 200? And maybe you conclude that it's not. And then your answer is, well, if it's not 200, what is it? And you could answer the question of what is the mean by asking for every possible thing you could imagine, Is it 200? Is it 201? Is it 202? Is it 203? And you could ask this question for every possible mean that you could think of and collect together all the ones where the answer is could be into a confidence interval. That's what a confidence interval is trying to do. That's why they're so strongly related, is because you can answer this question by answering lots of these questions. And so it contains a 95% confidence interval for the mean, contains all numbers where the p-value for the hypothesis, the mean is equal to that number, is under 5%. So you could actually imagine doing all those hypothesis tests one after the other and calculating all the p-values and all, no, not under 5%, over 5%. All the ones where the answer is, yep, could be that number. Because if this was under 5%, you'd conclude, no, can't be 200. But if it was over 5%, you'd say, yep, could be. Right, and so that 5% goes with the 95%. So if you wanted a 90% confidence interval, you'd get all the numbers where the p-value for the null hypothesis of being equal to that number is over 10%. Okay. And that is why a confidence interval uses the same symbols that are in the test statistic, because they're asking the opposite problems. The confidence interval is basically answering all of the hypothesis tests for lots of different numbers simultaneously, which is really cool, actually, I think. All right. So stepping back again, the endpoints of your confidence interval, I know that the ones that are inside the confidence interval, the p-value, if I use that as my null hypothesis, would be lower than 5%. Damn it, just a second. The ones that are inside, the p-value, if I use that as my hypothesis, would be above 5%. The ones that are outside, it would be below 5%. So the ones right on the edge are the ones where the p-value would have come out to exactly 5%. I'm just going to draw that picture again. These are numbers. It's like a number line. And all the ones, this is my confidence interval here. This one, the p-value would be below 5%. This over here, the p-value is also below 5%. And this bit in the middle, which I'll do it in a different color so that you know, it's greater than 5%. And these ones right on the edge, the p-value would be exactly 5%. That is one of the ways of thinking about what a confidence interval is. Why did I say all of that at this time? I said all of that this time because this T star, that's the T statistic that would go with a p-value of exactly 0.05. So that's my aside. I'll go back to where I was. 95% confidence interval endpoints. Where that T distribution, that T star, the p-value that would go with that T star is exactly 0.05 when I join these two bits together. That is what that T star is. Which means if you wanted to ask R what it was, you would have to ask it to tell you a T that goes with an area. Can I have a look at that exam again? I might be the Now, the t-distribution, the formula for the height of that curve is quite complicated, and it's very difficult to figure out what the answer is, and which is why we have to use a computer to do this sort of thing. You do not have a computer in your exam, but they will give you some helpful information. Give me a second. Yeah. See, in this exam here, they said, you just might assume that T star is 1.98. They just straight up gave you the answer. It's great. That was what I was looking for, to see how they told you. But they could also give you this information. You could ask R what this is. R is capable of, if you give it a value of T, it can tell you the area to the left of that. And if you give it an area to the left, it can tell you the value of T. And so if that's 0.05 on the outside, I'm just going to draw a new diagram just to make sure that we don't overlap too much and we can see it ourselves later. If that's 0.05 together, those two bits, this bit must be half of 0.05. Which means that this bit must be, like if this 2.5%, this would be 97.5%. And so I could actually ask R what QT of 0.975 is. Now I'm going to need one more piece of information here, and that is the degrees of freedom for my t distribution, because even though when I draw them by hand, I can't tell which one is which, computer knows. And so I have to put here a number which is the right number I need, which is n-1, I think. So this situation, yeah. Because we just have one list of numbers that we've calculated a mean from, and so we only have to take off one. So that would be 49. Was it 50? Yeah. Let's see, -1. So this, you would have to ask R what that was. Might as well just actually go and ask R. Of course, R always takes a little while to open. Yep, this gives me the T star. So I just note that in this practice exam, there was a question where they gave you a list of various R commands to choose from. You would go looking to find the one on the list that was the one you wanted, which would be the QT, whatever. And they might put in the PT as well, just to confuse you a little bit. They'll stick a few of the in there. So Q, yeah. You guys on the Zoom can't see this, but I don't feel like switching my window. It's not that important. 0.975, 49. 2.009575. That's what the computer said it was. So 2.01, maybe. 2 decimal places is pretty good, I reckon. What do you think? 2 decimal places? Okay. Kind of cool that it came out to be approximately 2. That's kind of nice. So you need to go looking for that. That was the only piece of information we didn't actually currently have in the original story. And so now we know that the endpoints are equal to x bar, which was 227, plus or minus t star, which was 2.01, times s, which was 12.3, over root n, which was root 50. And so I ask my calculator what both of those options are, one with a plus and one with a minus. Just before I say that, this thing here, that's the margin of error. Let's see what my calculator does. 227 minus 2.01 times 12.3 divided by the square root of 50. I don't need to put brackets around any of this because my calculator knows to do times before plus and times before minus. And so I get this answer, 223.50. And the other one with a plus, I've got a nice calculator that will allow me to replace this with a plus 230.50 when I round off to 2 decimal places. I don't know how many decimal places is reasonable. Actually, for grams, only 1 decimal place is probably enough, right? Grams is pretty small. They may have instructions on your exam as to how many decimal places they prefer. But if they don't, pick something reasonable. They're not really going to penalize you too much. They wouldn't penalize you. Obviously, don't round it off to the nearest 100. That's a bit ridiculous. Okay, and so that is my confidence interval. So they're the two endpoints. And so you would say that the 95% confidence interval is something like that, with a comma in between them. I don't know if you're supposed to put the grams inside that brackets or not. I always feel uncomfortable not putting units in. So it's never a bad thing to give it a go. So this is the picture here that I was talking about earlier. That's the 223.5 at this end, and that's the 230.5 at that end, and right in the middle is the 227. And we went up by whatever this works out to be, and down by whatever this works out to be. And that's how confidence interval is calculated. Now, obviously, in an exam, this would be much faster because you wouldn't be explaining it to someone along the way. But that's how the process works. And in an exam, they would have to tell you this information or just tell you, use the number 2.001 or whatever, which is what they did in this exam that you showed me here. They just said, assume that the T star is 1.98. Or they'd give you a list of R commands and you'd pick the right one. Okay. Would anyone like to say anything or ask anything about what I've just said so far? I haven't got up to the sample size calculation yet, but I am getting there. Yeah.
On that diet, like healthy diet. Yeah.
The margin of error is this distance.
Oh, yeah.
Margin of error. Yeah. It's how far up and how far down you go from the middle. So therefore, it must be the bit after the plus or minus because that's what we've done. We've added a bit and we've subtracted a bit. Okay. Very important question. Okay. So all of this is fine. I mean, technically it is related to the one sample t-test, but this is the confidence interval that goes with the one sample t-test. Yeah. So each hypothesis test has a confidence interval to go with it. And this is the confidence interval that belongs with the one sample t-test. Okay. Cool. And in fact, that was what was in my mind. I went, oh, well, if this was a hypothesis test situation, I have one sample's worth of data and I'm asking a question about a mean. And I don't know what the real standard deviation is because all I have is the one from the sample. And so that is what the one sample t-test is. And I use all the same symbols from the t-test to make the confidence interval. Because in the t-test, just as another aside, back here, they just The t-test would have been t equals x bar minus whatever the mean was divided by the s on root n, right? And these things are all in the same formula here. There's an x bar, there's an s on root n, and there's a t, and the mean is here, because that's what the confidence interval is trying to tell us. It's trying to tell us what the mean is. Yeah, so you can't see the mean in this formula because it's over here on this side. Yeah, but all those pieces are still there. And the reason it's plus or minus is because this t itself is positive or negative. Yeah. In the confidence interval for mu. The ends of the confidence interval for mu are this. So just so you can see all of the parts and how they join together. So it's very common for people to give in a course like this a table that just lists this thing and this thing and this thing, but doesn't give either of these formulas, and you have to know how to create them from the pieces. Yeah. Okay. Cool. So let's do part B of this example. Suppose the researcher wanted to estimate the mean weight, mean. So within, what were we within before? About 4 grams. To within 1 gram. With a 95% confidence interval. How many avocados would she need? So I have deliberately left a bit of information off that we need to answer this question, but this is a question that we could ask, right? So I'm going to think about what this means. When it says within 1 gram, that means that we're within 1 gram of the answer. It means the margin of error is 1 gram. We're going to say we need the margin of error to be equal to 1 gram. And I have a formula for the margin of error. It's this. That's what the margin of error is. It's this bit of the formula. So that answer has to come out to 1. And they're asking me, how big does n have to be to make that come out to 1? So there's actually quite a bit of information I don't know. I don't know what the sample standard deviation of my future unknown, like I'm going to collect some data and use the sample standard deviation from that data to find the margin of error. I don't know what that standard deviation is going to be. So I'm going to have to estimate it from the previous standard deviation that I already had. That's the best guess I've got. And I know that if I change the sample size, then the t-star is going to change as well, because changing n will change the degrees of freedom, and so the t-star will change too. And so I don't know what t-star is going to be either. It's really distressing. But that's okay. I can just say, well, it's got to be more than 50 because I didn't get to within 1 with 50. And so the T star can't be any worse than 2.01, because the bigger the sample size is, the lower that T star is going to get. And so this is my reasoning. So the margin of error before was about 4, I think, roughly 3.5. Yeah, definitely not 1. So the margin of error is how far apart these things are, the center and the edge, and the center was this, and that's about 3.5 away. So the margin of error before was about 3.5. So we're going to need a larger sample size. Which means a larger degrees of freedom. For the T distribution. And so a lower T star. So worst case scenario, it really is still 50 and we use the same T star we did before. So a lower T star. So if we use the old T star, it'll be at least an overestimate, right? It'll be fine. So use old T star and we'll overestimate. So that's my reasoning. You probably don't need to include all of that. And in fact, if someone gave you this question in the exam, they would just say it is appropriate to use the previous T star. Okay, and we'll also use the old standard deviation. And so now we've got 2.01 times the 12.3 divided by root n is supposed to be 1. And I have to use some algebra to solve that equation to figure out what n is. I don't know if this is what was in the course, but I do know it's something that is reasonable to figure out from the information we've got. So if I multiply both parts by the root n, that'll end up over here. And so I'll get 2.01 times 12.3 is 1 times root n. If there had been a number here, I would have had to divide by that as well. And then to get rid of the square root, I'm going to have to square it. And so I'm going to go for 612 just to be sure. Because if this was the correct answer, I can't collect 611.2 avocados. And going down wouldn't be enough. And so going up would be enough. So something like that. So I probably made one that was a bit harder than what's in the exam. That's my whole reasoning. If this was in an assignment question, I would put that entire thing in. In an exam, they'll probably tell me exactly which S and which T star to use in my calculation. How do people feel about this? Okay. So I guess, was it the bit where I was trying to figure out what to do with the T and the S?
Yeah.
Yeah. Because I don't know. You have to pick something. And usually the best thing to pick is the one you had last time, basically. And I reckon because that bit's a bit floppy and who knows what's going on in that bit, I didn't really know what I was doing either. So that's probably why I lost you. They would tell you what to do with that. But this bit here was me going, oh, well, margin of error's we need it to be smaller, so we're going to need a bigger sample size, which means we're going to need a lower t. Yeah. So anyway, that was my thoughts. So the bigger the degrees of freedom is, the lower that t star gets. That's just a useful thing to know about how the t star works. And the lowest the t star could possibly get for a 95% confidence interval is 1.96, which is the one that goes with Z. So I'm just going to just say that just as a note. For a 95% confidence interval, the lowest t star is 1.96, which is the Z star for a standard normal distribution. Just so you know. Because the Z distribution is the t distribution with infinity degrees of freedom. So I'm pretty sure, if I remember this course correctly, they actually put a formula straight in the notes for what the sample size is based on the margin of error if you know the standard deviation. So I'm just going to just say something. What if you knew the true population standard deviation? So what if instead of telling you that this was a standard deviation from the sample, they told you it was from the population? In that case, we wouldn't have done a t confidence interval, we would have done a Z confidence interval. So for example, you know, researcher knows standard deviation of avocado weights is exactly 12 grams. How many avocados are needed to estimate the mean weight to within, I'm going to give another number if that's okay, 0.5 grams. I wanted to make it slightly different so that you could see some of the working. But the main difference is that they know the true standard deviation of all avocado weights. So since they know the true standard deviation, they don't have to estimate with an S, which means they're going to use a Z instead of a T. That's one of the main decision-making processes. So since we know the true population standard deviation, which is officially called sigma, no need to use S, and so we'll be using Z and not T. So using this sample standard deviation S goes with using a T, using the population standard deviation sigma goes with using a Z. And so this time, the margin of error in a 95% confidence interval would be, now what was it before? It was T star times S on root N. So now it's going to be Z star times sigma on root N. Exactly the same as the previous calculation, but now instead of a T, there's a Z, and now instead of an S, there's a sigma. And for 95% confidence, Z star is 1.96, because that's how the Z distribution works. That's the lowest a T star could get, and it's the one you use for Z star. And so now I've got that the margin of error, which is 1.96 times 12 over root N, and I don't know what N is, has to be 0.5. That's what I've been asked. And so I can do all the same calculations. I can rearrange, multiply both parts by the root n. And divide both parts by the 0.5. And then square both parts. Now here I am. What is the 1.96 times 12 divided by 0.5 squared? Wow. Cool. So she needs 2,213 avocados, which is shockingly huge, but there you go, right? We halved the margin of error. So our previous one was like 600-ish. When you halve the margin of error, you quadruple the sample size. Because of this squaring here, that turns our ×2 into a ×4. Yeah. So the narrower you want that confidence interval, the more you're going to have to, the more sample sizes you're going to need. That's an expectation that we have. And if you halve the confidence interval, you're going to need 4 times as many. Halve the margin of error, you're going to need 4 times as many. That's a useful thing to know about how sample size works. If you ever have to calculate one, then you can say, oh, I really want it to be more accurate, but if you make it twice as accurate, you need 4 times as much. Yeah. I'm not at all surprised if in the notes there might be a formula, which is that n is z star sigma on margin of error squared. This may be in the notes somewhere, this formula, but it comes about from doing this same algebra. But I can't tell. A direct formula is this. And I've literally gone back here and said, well, that's the Z star, that was the sigma, and that was the margin of error, and just put letters in those spots. Yeah.
So doing that,
Yep. So instead of doing this algebra, you could have gone direct to here. Yeah.
And
that's for a Z confidence interval for a mean. In past versions of the course, this is the only time they've gotten you to do a sample size calculation. Again, I have no idea if it'll be in the exam, but at least we understand it better now. I was going to talk about that anyway, so I think we should talk about it now. Thank you. That's the thing I was thinking of. I'm just going to stop and number my pages so I don't lose track. And I'll be back in a moment. Okay. You really want to know how to differentiate between the different kinds of tests. That's really what that's the big question. So it might take me a little while, but that's okay. We've got nearly an hour. We can do it. More water. All right. Give me a moment to have a look at this. This was in the tute, I think. Yep. So test statistic confidence intervals stuff. And mostly the test statistics use the same symbols that the confidence intervals use. Yeah. Okay, there's a lot of information here. I think we're just going to have a look at this for a moment. I will say aloud, so whoever's watching the video, this won't be in the handout, like in the notes that I've got, but it is somewhere in your My Uni, in the week 12 content. Okay. So, oh, and look, you've even marked which tutorial they go in. That's kind of cool. Is that what this is?
Yeah, that's
Oh, that's just pleasant. Nice. That's such a Ben thing to do. I like Ben. Like I'm a big fan of the lecturer this semester. He does some useful things for students. Okay. Cool. Just looking at this, there are some similarities, there are some differences, many differences. Similarities are they all have a null hypothesis and an alternative hypothesis. In general, the null hypothesis has an equal sign in it, and the alternative has a not equal to. Sometimes the null hypothesis has a word, a string of words in one particular case. There's always some things you're supposed to check to be allowed to use the test. The assumptions, they all have a distribution to go with them. So I want to talk about some of those things. Like it was right at the very end. If I were lecturing this, I would be building this up as we went. But anyway, that. So really useful. Go find it. That's cool. All right. So this is all well and good. But the hard bit is telling which one you're supposed to use today. Yeah? So you can look at these and you can see the differences between them based on this table because they're all together. And you can notice that these ones use T's and these ones use Z's. And this one uses a chi-squared and this one uses an F. And so there's 4 different distributions that are involved. Can I show you something really stupid? See that normal distribution? The Z. Stupid. Anyway, helps me remember. Okay. And you can see that most of them are about means. There's 2 of them that aren't about means. Did you guys not do a 2 sample proportion test? You did? So this is not on this list, unfortunately. Okay. So this table doesn't cover all the tests. So that would have been Mel then. if it's a she, or could be anyone, you know. It's too many people. Like all the videos are lots of different people, right? Yeah. Okay. So, all right. So, two sample proportions. To be fair, you can use the chi-square test for that instead, but anyway, it's all good. Okay. So what you need is this is a good thing that can distinguish between the processes of actually doing the hypothesis tests, right? You can go, all right, this is what the null hypothesis is, and that's different to this null hypothesis. This is a distribution, that's different to this distribution. This is the calculation, it's similar to this one and different to this one. That's great. That's after the fact of choosing which one you've got. You can tell how they're similar and how they're different. But what you need is a way of telling the stories apart that you get told about the research. Each question in your exam, let's just have a look at this exam here. Each question in the exam says, research is interested in knowing blah, 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 blah. Oh, this one's a straight up maths question. Certain fish, we've got some questions about some fish. There's always a story, right? That they're telling you a story. You need to know how to distinguish the features of the story that help you decide which statistic go with it. And when you combine that with how to tell these apart this way, it can help you. Okay. So the features, first port of call is, if you're looking at your test statistic and you do not have the information mentioned there, then you can't use that one. So this one mentions a sigma, which is a population standard deviation. If they haven't told you that information, can't use this one. You have to use a different one. This one has a first mean and a second mean. If you don't have two means, you won't be using this one. So that's one very basic level of going, well, if I haven't been given that information, then I can't use it. That's useful stuff to know. Yeah. Okay. I'm going to show you something that I do to help distinguish between the stories. Oh, too late now, but goodbye, person who's leaving early. I'm never offended at people leaving. So this is not hard and fast method. Doesn't cover all possible situations, but it is useful for me. The things that help me tell the stories apart are the kinds of information that are recorded on the subjects of the experiment. And in particular, that's the general language way of talking about it. For a statistics way of talking about it, what kinds of variables have been recorded? They use the word variable, don't they? And you talk about categorical and numerical. That sort of thing, that makes a difference. And when I say subject, I mean whatever it is that the experiment is being done on. Avocados, fish, people, schools, petri dishes, whatever it is. You're going to need to know what kinds of variables have been recorded on each subject. And you need to know what the research question is. They spend a lot of time focusing a lot on figuring out what the null hypothesis is, because for many statisticians, that's a useful piece of information for them to figure out which test it is. So we'll talk about that, but you can't know what that null hypothesis is until you know what the research question is. And the research question will almost always be either about a specific number or about comparing the relationship between things. So it'll either be, just as the two options, it'll either be about a number or about a relationship. And most all, like all of your hypothesis tests except one, turn questions that are naturally, when you read the story, sound like they're about relationships. Statisticians turn questions about relationships into questions about numbers. It's just worth pointing that out. About numbers. And then the other thing that makes a difference is if you do have categorical information recorded, how many categories there are. That makes a difference. That in the light changed. And the last thing is, I just did this in an earlier revision seminar today, and I said it in a really nice way. So let me just check that. The heading that goes with this is called repeated measures or matched pairs, like that sort of thing. But the long version of it is, are different subjects, do different situations go with different subjects, or is every subject in multiple situations? That's the question. So different situations, different subjects, or different situations, the same subjects twice, or more than once. They are the four things that distinguish between the stories that they tell you about the research. Okay. And that stuff isn't really on this page, but that's what you want to know about. Okay. Let me talk a little bit about that. So basically, most of the different combinations of these are somewhere in this course. You've got about 1, 2, 3, 4, 5, 6, 7, 8, maybe 10 different hypothesis tests in this course. And they're based on different combinations of these things. Okay. So the kinds of variables that are recorded on each subject come in two kinds. And they spent the first week talking about kinds of variables, right? And they went, what's categorical and what's quantitative? Is that what they call it? Yeah. In my head, it's numerical because it's a number. But they call it quantitative, which is sort of Latin for numerical, So I'm just going to go back here. This is either category or right, categorical or quantitative. They're the two options back there. Okay. Here we go. I'm just going to start a whole new page, honestly. I might even start my numbering system again. Okay. So let me start by distinguishing between, oh, damn it, there is one more. There's just like, I'm really sorry, but it's the difference between the Z and the T is about one extra piece of information. So it's like, I'm sorry, all I can do is extra information that you know. Sorry about that. Man, I hate this anyway. Bear with me. Okay. So I'm going to talk about something. In the story that I had there before, you know, researcher, what was it they wants to, I'm just going to do this, wants to test to see if do have an average weight of 200 grams. They collect, 50 avocados and mean weight of the sample with an S standard deviation of 12.3. Do the appropriate hypothesis test, basically, that's the thing. In order to decide. Okay. Your lecture would probably give a much better final sentence than this, but that's what I'm going to do. So let's think about this story. You've always got to give your story a bit of grace. So I'm going to run through this set of questions. What kind of variables have been recorded about each subject? So first, you sort of have to know what the subjects are. So your subjects, the things that have had information recorded about them was avocados. And the information that we recorded variables recorded was their weight. Because we calculated a mean weight from the sample, so each avocado has a weight of its own. And that weight is a numerical variable. Oh crap, quantitative variable. Is a quantitative variable. And there's my question 3 is how many categories are there? That's not relevant because I don't have any categorical variables. And different situations is different subjects. Well, there's only one situation, so I don't have to worry about that. So there's only one situation. And that's useful, actually, how many situations are there in there? So it's not number of categories / situations, right? Only one situation, and don't really know any extra information. Haven't got any things like, population means or so population standard deviations or anything. I don't know any extra info. Now, I'm not normally writing all this down. This is what's going on inside my head, right? So let me think about, so I know because I've thought about this before, that I've got one variable recorded on every individual. I've got and they're all only in one situation, don't know any extra information. And the research question is of the flavor of, is the mean, the research question, is the mean equal to 200 grams? That's the question that was asked by the researcher. Is the average weight 200 grams? So this question is extremely similar to the answer of H0, mu equals the particular number. So one of the answers to the question of is the mean 200 grams is is this null hypothesis. And so it definitely goes with this sort of situation. And I don't know the extra information of the population sigma, so it must be this one. So, but from my perspective, it's much easier to think about it the other way around and to not try and compare to null hypotheses and just to go, okay, just a second. One variable measured on every individual, it's a quantitative variable. I'm interested in a number that describes that. Totally t-test for a single mean. That's the only option that goes with that. And organizing an extra column in this table maybe to describe the situation that it goes with might be a useful thing to help you. And so this is the picture in my head. This is my symbol for a quantitative variable. It's measured on a scale. And this was the weight. And I just want to know more about that. I want to know what the mean is. Which number? I want to know more about that number. And this picture says to me that. And if I drew this picture here, knowing that this picture goes with this story, that's how it helps me. All right. Let's do another example. Researcher studies pet ownership. I wonder if people who live in the suburbs more or less likely to keep their pets indoors, keep their cats indoors compared to people who live in the country. So even before I know any more information at this point, I can make a good guess at what hypothesis test would go with this. Ready? Well, maybe I'll add one extra sentence. A survey like 400 people and find that 30% of city cat owners keep their cat indoors while 20% of country cat owners do. Yep. I should probably say, note there's 200 from each region, something like that. Right, there's some information. So at the moment, I'm just going to do my 3 reads. the story is this. I wonder if people who live in suburbs are more or less likely to keep their cats indoors compared to people who live in the country. And then there's some details. And so we'll come back to that in a minute. Let's think about who the subjects are in this story. What things or people or animals are the subjects? Cat owners. Because we don't just, yeah, they're cat owners. They are the people, they are the things that we have recorded information about. That's who it filled out the survey. All right. What information do we have about our cat owners? We have where they live. So we have like the region. And is that a categorical or a numerical variable? With two categories, right? Two categories. They're either country or city, right? Or suburban. What else have we got? I didn't even know how to do this indoorsness, which is a categorical one as well. And it comes in flavors of yes and no, right? And that's pretty much everything we know about our cat owners, right? They haven't told us anything else. Okay, what's the research question? Yep. So are they more likely to keep them indoors, depending on the region? So I'm going to draw a picture of the research question. Ready? The research question is, does region, which comes in two flavors, make a difference to indoorsness, which comes in two flavors? That's what the research question is. That's a picture of it based on the variables we've got. So it's a relationship between two categorical variables. Now, there's actually two hypothesis tests that go with that. Look at this one. There is no association between the two random variables. You could totally use the chi-square test to do this if you wanted. Just wanted to point it out. It's a thing. You could also use the two-sample proportion test. They, in fact, answer the exact same question, which is confusing, and I apologize on your lecturer's behalf for putting such a confusing thing in, but they do answer the same question. The thing that helps me decide which one the lecturer really wants is that the extra information we have is already presented as percentages. Because the difference between this and the proportion test is that this one doesn't have any information here. This one doesn't use percentages. This one does use a p-hat, that's a percentage. It's a proportion, it's technically a decimal. And so that's the extra information. And so therefore I will do the two-sample Z tests. Why did I not fit this on this table? I didn't even write what this was. Sorry, this is a one-sample t-test back here. Two-sample Z test. But you could, if you needed to, do a chi-square test instead. They actually answer the same question. And not until I did this, when I first started doing this, did I realize they were answering the same question. But they are. They just use the information in slightly different ways. Raw numbers. So just as a pointer, we could do this, just this is actually how you would do it. You could say that P1 hat is 30% because of this 30% here, and P2 hat is 20%. And then our null hypothesis, we use that later, but our null hypothesis is that the true P1 is the same as the P2. I'm saying if, and so you know how I said we convert questions about relationships into questions about numbers? I'm saying, well, is there a relationship between these things? And if there wasn't, then these two percentages should have been the same. And so I ask myself, are they equal? And you should probably say where P1 is the proportion of city cat owners who blah, 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 and P2 is blah, 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 blah. You have to say what the letters stand for. They call that defining your parameters. Anyway, and so you could do that and you'll get a Z equals something with square roots and things. I can't remember the details. Or you could do the chi-squared test. And the chi-squared test would require you to create that 2x2 table that says exactly how many people are in each category. So you could say city, country, indoor, yes, and no. And we know there's 200 of each of them. Yeah. And we know that there's 30% of the city people, so this would be 30% of 200 here. So 30% of 200, but I guess, well, 30% of 100 would be 30, so this would be 60 people. And this would be 140. And this would be 20, so that'd be 40 people and 160. And so you could create this 2x2 table and then do the chi-squared test from there. You get to choose, but I have a feeling that if they really want you to use the chi-squared test, they'd ask you. Yeah. And this is slightly more work than this is because we've already been given them as percentages. And so, yeah, so this is the Z test for two proportions. So you get to decide what to do. I really like the chi-squared test, but the calculation's much harder than this one. So, yeah. So this decision here is not a decision about what the right thing to do is, it's a decision about what the easiest thing to do is. Yeah. But I knew it wasn't any of the t-tests because it wasn't about numbers, it was about categories. It wasn't about quantitative variables. And all of the t-tests are about quantitative variables. And I knew it wasn't the one sample proportion test because I had all of these people in two situations. This is my situation, right? Not all the people in two situations. Half the people in one situation and half the people in another situation. So because it was about two different situations, it wasn't the one sample proportion test because that's only about one situation. And those are the sorts of things that I would recommend thinking about. How are you feeling about what I'm saying here? So the pictures that go with the other ones, just if I'm going to add pictures to all of them. So the one sample Z test is this situation. That's it. There's only one variable and the question is what's the mean? But we also do know what sigma. That's my extra information. And the one sample t-test is one variable and we want to know what the mean is, but we don't know what sigma is. And the two sample t-test everybody has a single number recorded about them, but everybody's in two different situations. And there's different subjects in different situations. That's the two-sample t-test. So when you read the story and you go, oh, okay, so they've got my drugs. We've got a placebo version and a drug, and half of the patients get the placebo and half the patients get the drug, and then I watch them for 3 months and write down what their blood pressure is at the end. That's this story. Yeah. And then the question, of course, is like, is this related to this? But we pitch that as being about the means. So even though the original research question is, does the drug make a difference? You pitch it to be about means and say, oh, how could I ask that question to be about means or proportions or something? Oh, I could ask that as the mean of one, is the mean of one situation equal to the mean in the other situation? Yeah. Mm-hmm. Is this helping? Mm.
But you have the standard.
You have the sample standard deviation. You do need sample standard deviation. So so in the two-sample t-test, if you've got R, right, you don't have any of the means of standard deviations, you just got a list of data, right?
Yeah.
And so what the data looks like is there's like every person has which situation they're in one column and what the number is in the second column. But you normally do it from the two sample means and the two sample standard deviations, and you figure out the t statistic from there. Yeah. So exactly what information you use to calculate it is here in the table. And you're right, you can look to see what information you've got and going, oh, well, haven't got the right information to calculate that one. It must be something else. But just be aware that sometimes they might ask you, this is not an impossible question to ask, to say, here's a research story, which test would you do? And you go, well, seems like a two-sample t-test to me. And then they might ask you, what other information would you need in order to calculate this? And you say, oh, I need the sample standard deviations. That'd be a great exam question. I'd love it. You wouldn't have to actually do any calculations. You just have to say, t-test, this is what I need. Oh, that's so cool. I know I don't like writing exams though, because you're always in trouble from somebody. So, okay. So the next one is this same story. You are interested still in there being two situations. And finding out whether a number is different in those two situations. But this time, everybody's in both situations. And this is the paired or the matched pairs t-test. Some people just call it the paired t-test. In this course, it looks like they call it the matched pairs t-test. And it's worth pointing out that the matched pairs they're talking about are the pair of measurements that belongs to every person. So he's saying that everyone's in both situations, and I recorded the number twice, once in one situation and once in the other situation. And so what you actually calculate from this one is not the mean in one situation and separately the mean in the other situation. You figure out how far apart everybody's measurements are from each other and calculate the mean of that. So you find D is like x1 minus x2 or x2 minus x1 or whatever it is. And then do is the mean of difference 0, basically. So this is really interesting because it looks like this when you first start, but after you do the calculation, it becomes one of these, this one here, where instead of this, you end up with the difference in that spot. So some cool stuff. But the reason I have this is that if you're reading a research article, You don't calculate the differences yourself. You read a research article and you go, oh yeah, okay. So people were on the placebo and then they switched over 2 weeks later onto the drug, and I calculated their blood pressure in both of those situations. Sounds like a paired t-test to me. And when you go look at their stats section, it says, we did the paired t-test. Okay, cool. They've done the right thing. So you're allowed to use this information beyond this course to decide when you read research articles if they've done the right stats. Yeah. So that's the paired t-test. Well, so I'm just going to point out something out here. Damn it, I need to put it on the next page. It starts out with this. This is how the original story looks. That's my situation. But what you turn it into is what's the difference from every person's numbers? And you ask, what's the mean of that? You turn the data into this instead, and then that's the ordinary t-test technically. And that's why when you do it on the table here, it looks exactly the same as this one. It just has D instead of X because you're talking about the differences. Yeah. All right. So let's just note. So what's the next one on my thing? One sample proportion, right? It's just a category. You're either in it or you're not. And what you know is that there is a percentage that goes with the yes or the no. And you're saying like the proportion for yes. So when you look at the situation in a one sample proportion situation, you look at the information that's been recorded and you go, all they've done is write down a yes or no for every individual person. So when I think about all the people involved or all the animals or all the whatever's involved, there's just a yes or no for the individuals. And what they've given me is a percentage that goes with it. Cool. That's what the one sample proportion test is for. And it's to answer the question of, is the proportion equal to a specific number? So classic story would be like, we want to find out if all the children finished their homework on the majority of weeknights. So we surveyed parents and 55% of them said that they did. Is this evidence to suggest that more than half of children finish all their homework based on their parents' reports? And the answer is, you do the Z test and it would answer the question. And the two sample proportion is, well, you've got two situations and everybody's on only one of them. And you want to know whether that makes a difference to the yes or no outcome. And you specifically know it has percentages for yes in particular. That's what you're mostly interested in. Yeah. Now working my way down. Match pairs. Chi-square test is the exact same situation, but you can have as many categories as you want on both. No, exact same story, but you can have as many categories as you want on both sides. So the chi-square test, you've got as many categories as you want on either side. It doesn't make any difference. Like that. And does being in a different one of these situations make a difference to which category of those you end up in? So in your exam, your practice exam, yeah, that'd be great if I had the real exam. Everyone would want to come. There is one here that goes with that. A sociologist is doing a study. No, they didn't call her a researcher. Anyway, sociologist is doing a study to see if there's a relationship between the age of a young adult and the type of movie they prefer. So we're wondering is, if you've got a different age, does that make a difference to what kinds of movies you like? Like which one is your most preferred one? And this story is, well, we've got person's age, 3 options, being related to what type of movie it is, 3 options. And the subjects are people. And that is exactly what the chi-square test is for. Yeah. Now, I just want to say something really important at this point, which I didn't say earlier. Statistics can't actually tell which way this arrow goes. So it could go one way or the other, and so the stats can't tell you that. It can just tell you whether there appears to be one relationship one way or the other, but it can't tell you what causes what. Now, it is 100% false that the movies you like is what causes you to be a certain age. But you can predict someone's age from the movies they like, probably. And so this arrow is not about what causes what, it's about what you want to predict from what. So, yeah. And if you're not sure, it doesn't matter. You just be able to find out whether they're related. So that's what the chi-square test is for. So the 2-sample proportion test can be done with the chi-square test, but it only works when there's 2 situations here and two situations here. But you can have any number of situations on both sides. So, yeah, but this is a situation and this is a category that we record, and it's easier to think about it that way. So what's next on the list? ANOVA. One-way ANOVA. There is a numerical outcome recorded for every person, and there's just more than 2 categories. It's the same as the 2-sample t-test. It's just that there's more than 2 samples. And so when they do this story here, it's believed that the impact of different fertilizers affects the growth of plants in different ways. The test is claim a plant biologist randomly assigns 50 seedlings to 4 types of fertilizer. Okay, so just a second. Wait. We have 4 types of fertilizer, and we're wondering if it affects the growth. So in my story, that's fertilizer, and there's 4 of them, and they're not people, they're plants. So the picture that can I draw on this? So this is growth somehow. This is fertilizer, and the different plants are in different groups. And this number here is the dry weight. That's how this is how the researcher measured growth as dry weight. And that's totally what ANOVA is for. ANOVA is for when there's more than 2 groups and every individual is in a different situation and they all get one numerical measurement on quantitative measurement on every individual. And then when they did the ANOVA, it got this information and the p-value was low. And so we conclude that there is a relationship between fertilizer and dry weight. But statisticians like you to pitch it to be about means. We say, well, if there's no relationship between fertilizer and dry weight, all the means should have been equal. And so you say that the null hypothesis is that mu1 equals mu A is mu B is mu C is mu D. And it says define all the parameters used. You say where mu A is the mean dry weight for group A and mu B is the mean dry weight for group B and mu C is, and similarly for mu C and mu D. Yeah. But the alternative is that not all means are equal. And the only way to say that is with a sentence. Don't put crosses in there because that's ambiguous how to read that. So, yeah. So, but the point is that I knew it was ANOVA even before I read any of this stuff because I knew that there were 4 situations and a numerical outcome. Yeah. I didn't know it was going to, I wasn't sure it was a numerical outcome. If she had recorded it as got heavier or didn't, that would be a categorical outcome and I would have used the chi-squared test. Yeah. And then can I ask, does the phrase goodness of fit mean something to you? Nope. All right. Don't worry about it. In some courses, there's a second chi-squared test. Okay. So you know how we had the chi-squared test that went with this relationship? So there was a Z test that went with this relationship and a Z test that went with just one proportion. There's a chi-squared test that goes with one where there's more situations, and there's one that goes with several categories here as well. But I will not muddy the waters. So, and then the last thing is regression. And in regression, these are both numbers. Got two numbers recorded on every individual, and you want to know what the relationship between those two numbers is. And any later statistics that you might learn will fill in some of the missing combinations of these things. So the glaring omission that most people notice most obviously is this is similar to the to this. These two are similar. It's just that this is a number and this is a category. Why isn't there a paired version of this? Like with a matched pairs one of these. It's not in your course, but it does exist. So every combination does have a possible way of analyzing it. And it's just worth noting that that's something that you can ask. All right. I feel like the best thing is to stop there. We've done enough for today. I'm going to just, any questions or thoughts about that before we sign off? Cool. I'm going to stop the recording. There's no one in the Zoom, so I'll just turn it off.